Day 40, page 888, problem 42. Here's a good thought experiment, because obviously we don't have a 12-mile thick chunk of glass. But here we go. You shine light through this glass, and what happens is it slows down while it's in there, and it bunches up, so the wavelength shortens while the pulses are in the glass. I've tried to show you that with a diagram here. All right, it says in part A, how long does it take the light to transverse the glass? So that's a pretty easy, basically, V equals D over T problem. Because, well, first we've got to figure out the velocity of the light. It says, for the red light, N is 1.52, because it turns out that the index of refraction does depend on the color. For blue, it actually slows down more than red, and that's why you can separate colors with a prism by Roy G. Biv, because the light disperses. That's the separation of light into its colors, because the higher frequencies like blue slow down more, bend more if you project them at angles into a new medium. Here we're just going straight in, so they're not bending as they go in. I'm just showing you the wavelength nature of the pulse anyway. But the index of refraction for red is 1.52. For blue it might be 1.54. Not that much different. But let's see what happens here. So we got to go to the N equals C over V equation to figure out the actual velocity of the red pulse in the glass. So we have 1.52 equals 3 times 10 to the 8th divided by V. That V would be the velocity in this glass, which is 1.97 times 10 to the 8th meters per second. Now we use the V equals D over T. We have that velocity, 1.97 times 10 to the 8th equals D over T. Now 12 miles, if I did this right, is 19,300 meters. That's 19,300 over T. So figure out what T is. 9.80 times 10 to the negative 5th seconds. It's negative 5 seconds. That's how long it takes for the red to get through this theoretical chunk of glass. All right. How fast does the blue pulse travel? Okay, so part B here, it's traveling a little slower. It's not going quite as far in that same amount of time. So we're still going to use V equals D over T. V equals D over T. We're looking for V. It's only traveling, well, not the whole 19,000. It's getting, well, it comes up short by 1.8 miles, which is 2,900 meters. So if you take the 19,300 meters minus the 2,900, what's that give you? 16,400 meters. It goes 16,400 meters in the same time, the 9.8 times 10 to the negative 5th seconds. So the velocity of the blue is 1.67 times 10 to the 8th. That's substantially lower. 1.67. All right, you can figure out what percent lower that is. What is that, 30? And it's about 15% lower. It's not, I mean, it's substantial. All right, so now we got to figure out the index of it says we could figure out the index of refraction for blue now. If you wanted, didn't ask us to do that, well, that would have been a good question to ask. Just do N equals C over V. Given that V, you'll find out that N will be greater than 1.52 for the blue. But it asks you how much time will elapse between the red and the blue emergence. Well, okay, so it's just another V equals D over T problem, because the blue still has to go 2,900 meters. It has to go 2,900 meters yet. We're looking for the time. You're going to take this velocity. I'm out of space. You can do this. Plug in that velocity. How much time will it take for the blue to travel that final 2,900 meters, and that's the final one. It did also mention that Albert Michelson observed this effect in carbon disulfide, but he didn't have a 12-mile chunk. He somehow observed this in a smaller chunk in a laboratory that red and blue going through some carbon disulfide, the red pulse comes out first. Be an interesting lab or experiment to Google and see more information on that.